Which of the following concepts explains Markovnikov's rule as applied to the addition of hydrogen bromide to propane? A. The relative stability of the carbocation. Now, Markovnikov's rule is about the stability of the carbocation, which is the intermediate product formed in the reaction. So the answer is A. But let's look at the other answers. Nucleophilic of the bromide anion. That is not the answer. So we could demonstrate this. This is propene, and then this is hydrogen bromide. So this nucleophile will pick this proton, moving these electrons to the bromide atom. So in the intermediate that is formed is this secondary carbocation. We could have formed this secondary carbocation, or we could have formed this primary carbocation. So between these two, this is secondary carbocation and primary carbocation. Now, secondary carbocations are more stable than primary carbocations. So the reaction is favored by the relative stability of the carbocation. And we also have here the acidity of the hydrogen bromide. That is not one of the answers. And solubility of propene in aqueous medium. It's not about solubility. And the nucleophilicity of the bromide anion. It's not also about the nucleophilicity. Which of the following concepts explains why tertiary carbocations are more stable than primary and secondary carbocations? So we have here electronegativity. It is not about electronegativity. And then B, tautomerization. It's not also about tautomerization. And then C, hyperconjugation. So the answer is hyperconjugation. And then D, octet rule. And then E, electrophilicity. Which of the following is not true regarding alkenes? A, alkenes are non-polar. That is true. Then B, alkenes burn in air to give water and carbon dioxide. That is also true. All the hydrocarbons burn in air to give water and carbon dioxide. And then C, alkenes are highly miscible with water. Now, these two statements are contradictory. If a compound is non-polar, water is a polar solvent, and therefore it cannot be non-polar and also be miscible with water again. So if this is true, then C is not true. Then the other answers are the strongest intermolecular force between alkene molecules is the van der Waals forces. And then E, they are very reactive compared to alkenes. So it's none of these. The correct answer is alkenes are not highly miscible with water. But here he says that they are miscible with water because alkenes are non-polar. Which of the following statements is not true? A homolytic cleavage of a bond in a neutral molecule gives two radicals. That is true. Radicals have unpaired electrons. That is also true. Movement of a single electron is depicted using the fish arrow, and that is true. D, the carbon fluoride bond is the weakest bond between carbon atom and a halogen. This is not a true statement. But let's look at the last answer. Heterolytic cleavage produces ions. So that is true. So if A is true, B is true, C is true, and E is true, then the only one that is left is D. However, let's analyze it. It says that the carbon fluoride bond is the weakest bond between carbon atom and then a halogen. Now, remember that in the periodic table, it is from fluorine to chlorine to iodine, then to bromine. Now, based on periodic properties, then as going down the group, the atomic size, the radius increases. And for that matter, the bonds become weaker as you go down the group and not rather stronger. What is the IUPAC name of the following compound? Now let's name this compound. So this is 1, 2, 3, 4, 5, and then 6. So we have a 2-methyl. And since the number of carbons on the parent chain are 6, then we are talking about hexene. And also the double bond is on carbon number 2, so it's a 2-hexene. So the name is 2-methyl. Sorry. And then also there's also a methyl on carbon number 4. So there's also a 4-methyl. So at the end of the day, we are going to have a 2,4-dimethyl and then 2-hexene. So the answer is C. E is 2,4-dimethyl 2-hexene. What is the relationship between the following pairs of structures? Now, if you look at this structure, you will see that they are enantiomers, but they are not mirror images. Because if you put a plane of mirror here, this side is a methyl, but this is a proton. And then this other side is also a C3, but this is a chlorine. However, you can see that the arrangement of substituents on this molecule is the same as the arrangement of substituents on these molecules. There are 2 chlorines. This one also has 2 chlorines. And this one has 2 methyls. There are 2 methyls here. And there are 2 carbons, 2 carbons, 2 protons, and 2 protons here. So these are enantiomers that are not mirror images. And therefore, these are diastereomers. So enantiomers that are not mirror images are known as diastereomers. And therefore, the answer is B. Which of the following compounds has only primary and tertiary carbon atoms? So we have a hexane. Let's draw a hexane. 1, 2, 3, 4, 5, 6. So this is a hexane. We also have 3-methylpentane. So this is a pentane. 1, 2, 3, 4, 5. And then it's on 3-methylpentane. And we also have 2-methylpentane. So this is a pentane. And then we have a methyl group on carbon number 2. And we also have 2,3-dimethylbutane. So this is a butane. 2,3-dimethyl. And then a cyclohexane. This is a cyclohexane. Now, let's start with the cyclohexane. You see that it all has 2 protons here. So there are 2 protons each on each carbon. So CH2 is what? It's a secondary carbon atom. So therefore, all of this are what? Secondary carbon atoms. But we are only looking for the primary and then the tertiary. So the cyclohexane is out. Now let's come to the hexane. And with the hexane, this is a primary carbon and this is a secondary carbon. So we only have primary carbons and then secondary carbons in hexane. But we are looking for primary and tertiary, so hexane is also out. Now let's come here. This is a primary carbon. This one too is primary and this is primary. This is a secondary carbon. And then this is a tertiary carbon. But we are only looking for primary and tertiary. But there are secondary carbons here, so that's also out. If we come here, this is a primary carbon. This is a tertiary carbon. This is a primary carbon. Secondary carbon, and a primary carbon. So there is a secondary carbon here. And for that reason, that can also be part of the answers. So the only answer left is the 2,3-dimethylbutane. However, let's see whether it's true or not. This is a primary carbon. This is primary. This one too is primary and this is primary. This is tertiary and this is tertiary. So you see that it only contains primary and tertiary carbons. That's why it's the correct answer. In halogenation of methane, the reaction below is associated with. Now, you see that this is a propagation step because we have a radical that interacts with halogen gas and then that halogen, it will give us a halo alkene and then radical. So this is a propagation step. For that matter, the answer is B, propagation step. What is the configuration of the two chiral centers in the following molecule? Now, if we take here, you see that this is a chiral center and this is a chiral center. Now, if we start with this one, you see that this place is carbon number 1, and then this is carbon number 2, and then number 3, and then the proton is carbon number 4, and it is on the dash bond. And for that reason, this is 1, 2, 3. So it is moving in the anti-clockwise direction, and therefore this is an S. Now, if we come here, this is 1, this is 2, this is 3, and then this is 4. But the least group, which is this metal group, is not on the dash bond, and therefore we will invert configuration in this case. So you see that if we check this one too, it's moving in the anti-clockwise direction. So that is S. But because we are supposed to invert configuration, this is an R. So now we have, if we were to assign numbers to the carbons too, this will be 1, this is 2, this is 3, 4, 5, and then 6. So we have a 3R and then a 5S. So 3R and 5S. This is a 3R and then a 5S. So the answer is B. What is the correct order of stability of the following radicals from the most stable to the less stable? So you see that this is a primary radical, this is a secondary radical, and this is a tertiary. Sorry, this is a tertiary radical, and this is a secondary radical. Now, in terms of radicals, primary radical is less stable than secondary radicals, and secondary radicals is less stable than tertiary radicals. So in order of most stable to less stable, then the most stable is number 2, because that is the tertiary radical, then followed by number 3, and then followed by number 1. So it's 2, 3, 1. So 2, 3, 1. So the answer is E. What is the major product obtained from the following reaction? So this is a hydroboration reaction. And hydroboration reaction is an anti-Markovnikov's reaction. So we are going to produce a primary alkene. So this is an OH, but the number of carbons are 4. So 1, 2, 3, 4. So this is what we are going to produce in solution. However, this will not stay like this in solution. What will happen is that there will be tautomerization. So let me show the tautomerization. So let's say the proton is here, and then the alkene is here. So what will happen is that this alkene will pick this proton, forcing this to move here. So at the end of the day, we are going to get this product. And this is a butanol. So the answer is A. So butanol. Which of the following is not true regarding the formation of substituted cyclohexanes? A. Ring inversion of cyclohexane between two chair conformation take place through the boat conformation. That is a true statement. And then B, he says that substituted cyclohexanes are destabilized by 1,3 diaxial interaction. That is also true. Then C, the boat conformation of cyclohexane is more stable than the chair conformation. This is not a true statement, because the chair conformation is more stable than the boat conformation. And then the D is the relative amount of two conformations of substituted cyclohexanes can be determined from the difference in strain energy. That is a true statement. And then it says that the equatorial positions are more stable positions for substituent. So this is also a true statement. Which of the following compounds is or are chiral? So we are looking for the chiral compounds here. And let's take this one. Let's redraw this. So this is the carbon in front. It's bonded to a bromine and then a proton. And then it's also bonded to a methyl group. So let's assume the methyl is a CH3. Now, the carbon at the back is this one, this carbon. And that is bonded to a CH3, this CH3, and also bonded to another CH3, and then a proton. So let's put the proton here. Now, is there a chiral center here? This is not a chiral carbon because of these two metals. Nonetheless, this is a chiral center because there's a bromine here, which is different from this carbon because this carbon is bonded to two methyl groups, and then which is bonded to this carbon and a proton. So this molecule is a chiral molecule. And let's come to this one. Let's draw the carbon in front. It's bonded to a proton and then a bromine group and then a CH3. So let's show the CH3 here. And then let's draw the carbon at the back. So this is the carbon at the back. It is bonded to, sorry, it wasn't complete. There's also a proton here. It's bonded to 3 protons. So there's 1 proton, 2 proton, and then the third proton. So you see that this is CH3 and this is CH3. They are the same. And because this is CH3 and this is CH3, this is not a chiral compound. So 2 is not a chiral compound. Now let's come to 3. If you consider the 3, so let's draw this carbon. This is this carbon here. And then it is joined to a CH2, CH3. So CH2, CH3 is here. And it is also joined to a CH3 on this side. So this is CH3. And then there are 2 protons here. This is a proton and this is also a proton. So you can see that this molecule too is not a chiral center. Sorry, you can see that this compound too is not a chiral compound because it doesn't have a chiral center, and therefore the answer is only one, only A. Which of the following is the definition of a pair of diastereomers? A pair of structures that are superimposable mirror images of one another. That is not true. B, a pair of stereoisomers that are non-superimposable mirror images of one another. This is not also true. And C, a pair of isomers that are not mirror images of one another. So C is the actual definition of diastereomers. Diastereomers are mirror images. They are isomers, but they are not mirror images of one another. The hybridization of the central carbon in CH3 C triple bond N and the bond angle CCN are. Now, since this is a triple bond, then the hybridization is an sp hybridization. Now, every sp hybridization is 180 degrees in terms of bond angle. So it's an sp hybridization and it's 180 degrees. So this is sp hybridization and 180 degrees. So the answer is B. Which halogen is most useful in the regioselective radical halogenation of alkenes? A, fluorine. B, chlorine. C, bromine. D, iodine, and none of the above. It is the bromine. The reason is because the bromine can undergo the Markovnikov's reaction, and it can also undergo the anti-Markovnikov's reaction. So that is why the bromine is the most regioselective. Choose the odd ones out of the following structures. So let's determine the configuration here. So you see that this is an A, it's in the axial position, and this is in the equatorial position. So this is, and it is 1 2. So this 1 2 is a 6. AE in a 1 2 interaction is 6. And this is also in the equatorial position, this is in the axial position. So this is EA, and it is a 1 2 interaction. So this 1 2 is also a 6 interaction. Now let's come to this. We need to draw this in terms of a boat conformer. Sorry, in terms of a chair conformer. So let's draw this chair conformer. So now this is the carbon in front. This is a carbon in front. So if we stand here looking at this molecule on this side and we use our hands to hold here, you see that this is the carbon in front. This is the one in front. And these ones are at the back. So now with the carbon in front on the side, there is a proton. That is, this proton is this one. And then there's a proton coming down here. And then there's also, and there's this proton which is going up. So, but in this case, it's going to come down. And then it is linked to a CH2. This is the CH2. Now, if we come to this one, there's this methyl group. So this methyl group CH3 is here. And then there is a proton. This proton is the one here. And that is also linked to a CH2. This CH2 here. Now, if we come here, the one at the back, which is this one, there is a proton. So this proton is the one here. And there's also a proton here. And that is linked to a CH2. So this CH2. And if we come to this one, we have a CH3. So the CH3 is here. And then we have this proton, and that is linked to a CH2. Now, at the end of the day, what is this interaction? You see that this is in the equatorial position, and this is the axial position. So it is EA. And EA in a 1 2 interaction is also a cis. So this is also a cis. Now, this is a 1 2 interaction. And then you can see that this is a wedge bond, this is a dash bond, but this is a trans. So this is a trans molecule. So of all these molecules, this is the only odd one out, which is 4. So the answer is D.